Welcome to Math331, the little questions. This is lecture 12. I want to finish the sums of squares problem and use this to talk about some related problems about how do you estimate an answer, how do you get a sense of when something is possible, how far can you push some of these elementary methods. And again, I've mentioned that if anybody's interested in writing any of these up, either just for fun or instead of doing, the midterm exam, I think a lot of these would be really good things to write up and put in the literature. So for example, I don't know if the argument we're doing has ever been done in terms of just trying to use the pigeonhole principle to prove there have to be at least two sums of squares that align. And we were just barely failing where class ended last time. We got, there was a missing a factor of 2. I claimed it should have been pi over 8. We were getting pi over 4. Here's the missing factor of 2. And I'll put it in purple to emphasize it. When we were counting pairs with a less than or equal to b, when we did the sum like this, b goes from 1 to root x, a goes from 1 to square root of x minus b squared, that doesn't force a to be less than b. So that's really counting all the pairs that have a squared plus b squared at most x. So how do I get rid of the double counting? What's the easiest way to get rid of double counting in the sum? So does everyone agree that this sum is going to double count? It's looking at all pairs a and b such that a squared plus b squared is at most x, not all pairs a and b with a squared plus b squared at most x and a at most b. So I'm double counting. Approximately, what do I need to do to get rid of the double counting? Yeah, just multiply by half. It's not perfect because if a equals b, I shouldn't multiply by half. So this has a slight issue, slight issue if a equals b less than or equal to square root of x, but only root x such items. And that's lower order. So even though we're off by a little bit, if we put in a factor of 1/2, we're off by a lower order term. We're off by square root of x. So you can make all of this rigorous, but does everybody understand that we were double counting by this extra factor of 1/2? And now by putting the factor of 1/2 in, everything is fine. So I just have to keep putting in 1/2s in all of these places. So this is where it's really nice to just be able to go through the slides and just put in the 1/2 and fix things. And there's an extra 1/2 now. And now we're no longer missing a factor of 1/2. I can no longer erase that, unfortunately, for some reason. So I'll say found the missing factor of 1/2. I'll make that into an exclamation point. So it's pi over 8, which is about 0.392699. So another way of looking at this is if I look at all the pairs a, b, such that a squared plus b squared is at most x, I want a to be at most b, so I'm not double counting. I don't want to count 3, 4, and 4, 3 as two different sides. How many such pairs are there? About 0.392699 times x. So as x grows, not surprisingly, we get more pairs. And the number of pairs grows linearly with x. It grows like about 39.26%. And then we did some arguments before about, what were the possible numbers of distinct residues for a squared plus b squared mod m for different m's. And this is where we want to use the pigeonhole principle. Imagine that there was only one possibility for a squared plus b squared mod m. Say we take m equals 100 and there's only one possibility. Then that means out of every 100 consecutive numbers, only one can be hit. And for the next 100 numbers, only one can be hit. And then for the next, only one can be hit. And so if we have too many possible pairs of a and b, then at least two pairs have to go into the same value. What if only 0.00005% of X was how many we had. Well, then if we're only getting 1%, then it's possible that they're all distinct. But if we were getting 3% of X and only 1% are admissible, we have more pigeons than boxes and we win. So we needed to show that there was fewer boxes for things to land in than elements that need to be landed. Okay, so that's the big idea here. And we looked at a couple of powers of multiples of 72. And it seems for some reason that multiples of 72 work really well in having fewer possibilities for the remainder when we add two different sums of squares. These were the ones that were coming in under 50%, and we got 41.31%. And we needed to get to 39 point something, so we were just missing. Again, we looked at powers of 2. It looks like powers of 2 are always going to be above 50% and coming down. This is actually not that bad of a calculation to do, because when you're looking at powers of 2, it's really nice to see how they will interact. You know, we'll have 0, 2, 4, 8, 16. And when you add, it's not going to be too bad to look at what arises. For other numbers, it's going to be much harder. And so, you know, we looked at lots of data like this. We saw a few things that got really close to that 39%. And so the best one we saw was at 576. It was 40.104. And we needed 39.26. So did anybody write any code to see if you could go further?
I just got anything, but I didn't.
So I already had the code.
Well, I was gonna go 100,000.
So, you know, again, we need to get to 39.26. I wrote the code, and at 2304, I had success. So at 2304, only 39.1927% of the residues are possible when you look at sums of squares, mod, you know, 2304. And since we have 39.2699 x going into just 39.19 x, at least one thing has to be hit twice. So there has to be at least one hypotenuse that has two fundamentally different bases that work. That doesn't mean that we have two different Pythagorean triples that have the same hypotenuse, because we're not requiring that the hypotenuse be an integer. We're not requiring that a squared plus b squared is c squared. We're just requiring that we have two things that work. So I found it really interesting that it just barely works out. It's fascinating by how small of a margin of victory we have. If anybody plays professional sports or anything like that, it's oftentimes amazing how well things are calibrated so that things are interesting. You know, first base is just far enough away that it's exciting to get there. And it's not too easy, it's not too hard. Same thing for stealing, same thing with so many different things. It's trying to find that sweet spot so that things are interesting. You know, here, things were just barely missing, but they were missing by so little that there was hope that we'd be able to find something without going too far. One of the slides, if you haven't seen this before, it's the Online Encyclopedia of Integer Sequences, the OEIS. If you have a sequence of integers, you can input that to this website, and it will tell you everything it knows. And so what I did is I inputted the first few values that had less than 50% for the number of residues for the sums of squares. You know, is this anything interesting? And the answer was, sorry, but the terms do not match anything in the table. The following advanced matches exist for your query. It's the Beatty sequence, the floor of n times z with 72 over 1 is less than or equal to z is strictly less than 721 over 10. And the next few terms do amazingly match the next few terms in the sequence that I have. Do you notice anything interesting about the number that arises here? That's related to a comment that you guys made as to where we should be looking. What numbers were we searching, trying to, yes?
I think it's like 2 to the third times 3 squared.
Yeah, and what number is that?
72.
And look at what it's getting. Yeah, it's somehow detecting that there's something related to multiples of 72 coming into play here, which is absolutely amazing. One thing you could do is you can create your own sequence. You could say, what I'm going to do is I'm going to look at all the moduli, and every time I come up with a moduli that has a lower percent of realized residues than anything to date, I'm going to call that the new champion. And I'm going to have a list of champions. So people are champions for a while, and then something new comes in. So the first champion would be basically either 1 or 2 by default. And then maybe 4 comes in. And then it takes a while before we finally get, a champion that's below 50%. None of the powers of 2 work. Over here, where do you think the first number below 50% is? 72. But if we look at this, other numbers would be champions. And so over here, this is probably the first champion. And it will hold for a little bit, and then this becomes the champion, and then this becomes the champion, and then this becomes the champion. And then here's the champion, here's the champion, here's the champion. And so those could be a sequence of champions. And then the question is there anything interesting about the numbers, about their prime factorization as to which numbers become champions and why? You could also ask, how long does your reign last? In the beginning, your reign is lasting not that long. Does the reign always last longer than the previous reign? No. So good. We don't have to go that far to disprove a conjecture. It looked like the reigns were getting larger. Maybe the range is approximately doubling. But we have, something going on over here where it's a really short reign. Why? What's going on? This is how research happens. You start noticing things, and then hopefully you notice things that people care about, that there's something interesting going on. So anyways, there's a lot that you can do with this problem. I just wanted to point these out to you. Okay. So we talked about how we won. Okay, so now we can look at some other related questions. So we've talked about, is every number a sum of 2 squares? So is every n a sum of 2 squares? And we proved that the answer is no by just looking at remainders, right? We saw that which remainder you're never going to get for sums of 2 squares. You need to give me a modulus and a remainder. So the modulus was 4. When you look at the sums of squares mod 4, what don't you ever get? So what are the squares mod 4? Mod 4 squares are 0, 1 squared is 1, 2 squared is 0, 3 squared is 1. So sum of 2 squares is 0, 1, or 2 mod 4. So never get 3 mod 4. So this is a really simple proof that every number can't be written as the sum of 2 squares. We can't ever get a number that's 3 mod 4. If we looked at remainders modulo 8, we could even get a better result. Even more numbers are not. Then the question is, can you find something below 50% so you can say a majority of numbers can't be written as sums of squares? And it took a while, but when we got to 72, we finally got a number that was enough to tell us a majority of numbers don't have this property. It might be the case that in the limit, almost no number is the sum of 2 squares. Just because we're seeing a lot of numbers that are potential, that doesn't mean they actually arise. It just means we can't eliminate by this. So what I want to do is I want to count how many numbers do we have. that squared is something at most x. So this is similar to what we were doing before. So let's say ab less than equal to x, and we want a squared plus b squared less than equal to x, and a less than equal to b. So the question is, how many ways can we choose two such numbers? And this is the calculation we were doing before. So this is where we got the, 1/2, the sum b goes from 1 to the square root of x, and then the sum a goes from 1 to the square root of x minus b squared of 1. And then let's subtract off the double counting. And the double counting is the sum b goes from 1 to the square root of x of 1. That's from the double counting. So does everyone agree that this is the quantity we looked at before? This was basically some constant times x. This is going to be some constant times square root of x. In the limit, as x gets really large, the second piece doesn't matter. So if I'm trying to look at representing numbers as the sum of two squares, the diagonal piece, the time when a equals b, is insignificant. What if I just chose ab less than equal to the square root of x? How many ways can we do that? I want to choose two numbers at most square root of x, and let's say I want them distinct. How many ways can I do that? So how many ways can I choose two numbers at most x that are distinct with a less than b? So this is a problem you know. I'm just asking you maybe in a way that's not resonating. This is something you've seen in probability or combinatorics. It's just square root of x choose 2. And now we want to choose a equals b less than square root of x. How many ways are there to do that? Right, but how should I write square root of x? I should write it as square root of x. Similar to the first one was root x choose 2. How should I write this? Yeah, root x choose 1. It's sometimes easier to write this way to highlight what's going on. This is basically root x minus 1 over 2. This is root x. So the sum is basically going to be root x plus 1 over 2, which is basically x halves. So what this tells me is if I look at all the pairs with a and b at most root x, with a less than equal to b, I only get x over 2 pairs. So what's the maximum number, what's the maximum percent of numbers that could be the sum of two squares? So what's the maximum percent of numbers that could be the sum of two squares? A half, right? Because this only gives me a half of the pairs. Notice, however, that if both a and b are very close to root x, then the sum of their squares is going to be larger than x. So I expect this to be a very bad result. This simple argument tells me not only is every number not representable as the sum of two squares, but I think that the percent of numbers that can be done as the sum of two squares is going to be less than 50%. Instead of using sums of two squares, what could I try to do next? So instead of trying to write a number as the sum of two squares, what would be the next thing to try? Sums of three squares. Do you think every number is the sum of three squares? Is every n a sum of three squares? We could, first of all, we could try to do the calculation as before. We could look at, maybe the sum, c goes from 1 to the square root of x, then the sum b goes from 1. How large could b go to? So we want a squared plus b squared plus c squared to be less than or equal to x. So how large could b equal? I give you a value of c. What's the largest b could equal? This
So,
x minus c squared, right?
oh yeah.
So this is a multivariable calculus. We're finally using it. And then how large could a be? The square root of x minus, yeah, or b squared plus c squared, however we want to. So that would be the sum we would have to figure out. But that's going to count a couple of things too many times. What should I divide this by? So if I give you a triple A, B, C, how many ways are there to permute the triple? So how many ways can we permute the triple A, B, C? 6. 3 factorial, or 6 ways. So what do you think we need to do over here? Divide by 6. And then this will be basically, this is counting maybe distinct triples deal with the lower order of 2 the same or 3 the same. If all 3 of them are the same and you want the sum of their squares to be at most x, how many such triples are there? So how many triples would there be if they're all the same and a squared plus b squared plus c squared is at most x? So we want a squared plus a squared plus a squared to be less than or equal to x. How many choices are there? Square root of x over 3. Even if you didn't have this over 3, what we know is that the number of choices is going to be growing like the square root of x. That's much smaller than something of size x. So, the challenge is to prove that that integral, that triple sum is really like an integral, is really of size x. Then, of course, you have to estimate, well, what happens if 2 out of 3 are the same and 1 is different? And again, you want to show that that's a lower order term. What you're going to get here is that there's just too many triples. So what if we looked at A less than or equal to B less than or equal to C less than or equal to, say, square root of x over 3. What can you tell me about a squared plus b squared plus c squared? So if each one of them is at most the square root of x over 3, what can you tell me about this sum? Is at most x. So if I count how many triples are there with a, b, and c at most square root of x, and a less than equal to b less than equal to c, that's going to be a lower bound on how many triples. So this is going to give us a lower bound. So we want to choose 3 integers from 1 to ... square root of x over 3. How many ways are there to choose 3 integers from that set? So how many ways can I choose 3 numbers, distinct? Square root of x over 3, choose 3. And this is approximately root x thirds cubed over 3 factorial, right? So again, go through and do the rest of the calculation, look at the lower order terms, but the first term is going to be square root of x thirds. The next one is going to be 1 less than that. The next one is going to be 1 less than that. All right, when x is big, they're all basically root x over 3. So this is going to give you x to the 3 halves over 27 times 6. We'll just leave it as 27 times 6. Or I can write this as x to the 1/2 over 27 times 6 times x. So this gets large. So I'm never going to be able to show that not every number can be written as a sum of 3 squares by trying to do a similar argument to what we just did. There's just too many possibilities. Whenever you're doing something, it's good to get a sense of where do things break down. Yes?
27 times 6.
I'm sorry?
Was it 27 times 6?
Oh, sorry, it's not 27 times 6. It's the cube root of 27 times 6.
Okay.
Sorry. So that, you're right, this should be the, sorry, the square root of 27 times 6, right? Yes, sorry, it's the square root of 27 times 6. Because the 3 is inside the square root. Yes. The important thing to note is that we have too many triples. There are going to be too many possible items. So a pigeonhole argument will not work. And this is as important of a skill of learning when something works as learning when something will not work. That it makes no sense to try to make a pigeonhole argument work here. There's just too many objects. It's not going to be successful. This doesn't mean every number can be written as the sum of 3 squares. It just means I can't disprove it using the same methods I did a moment ago. A moment ago, we were able to show not only can every number not be written as the sum of 2 squares, but we can go back far enough, but in fact, we think a majority of numbers cannot be written as the sum of 2 squares. This gets us just barely 50%, but a lot of these tuples, the sums of their squares is greater than x. So how might you try to attack is every number expressible as the sum of 3 squares? So the pigeonhole principle failed us. Do we have any other way that worked to show that not every number was the sum of 2 squares? Mods. So let's try mods again. In the interest of time, do you want to try mod 8 or mod 8?
What's the mod 8?
Let's do mod 8. Okay, that's fine. Which mod 8 did you want to do? The first mod 8 or the second mod 8? Second mod 8. Oh, interesting. Look at sums of squares mod 8. So here's n squared. So 0, 1, 2, 3, 4, 5, 6, 7, 8. 0 squared is 0, 1 squared is 1, 2 squared is 4, 3 squared is 9, which is the same as 1. 4 squared is 0. 5 is the same as 8 minus 3. And so when I square things, the minus sign doesn't matter. So 8 minus 3 squared is the same as 3 squared, which is the same as 1. So I just write things in reverse order now. So now we have 0, 1, and 4 plus 0, 1, and 4 in hopefully obvious notation. What are the possibilities? 0, 1, 2. Before 5, we have, what do you have before 5? 4, 5. So that was the sum of 2 squares, right? Now, what if we do sums of 3 squares? So now let's do plus sums of 3 squares. Now we have 3 choices for the first, 3 for the second, 3 for the third. That's 27 things to look at. But again, a lot of things are going to be the same. You have the 6 ways of permuting things that are distinct. So what's the smallest I could get? 0. I could get 1. I can get 2. Can I get 3? Yes. Can I get 4? Yes. Can I get 5? Can I get 6? Can I get 7? No. Do you think we would get a contradiction if we looked at things mod 4? No, and that's probably why I said, do you want to do things mod 8 or do you want to do things mod 8? Right, in the interest of time. But you start off with a smaller calculation. This is already enough to let us know that we cannot write every number as the sum of 3 squares. And in fact, a positive percent of numbers will miss. The density argument is not strong enough to do this. There's just too many possibilities. But the congruence argument is enough. So again, if anybody is interested in trying to write this up, the fact that it's so close to pi over 8, and it takes a while before we finally get something that is just a little bit smaller, and we can use the pigeonhole principle, I found that really interesting. So again, this day now gives us an opportunity to talk about pigeonhole principles. So I just pulled up, 4 problems. I will give people a moment to just take a look at these. I'll read them, and then if there's anything that people found particularly interesting, we can do that. So the first one is we take a subset S from the numbers 1 to 2n. If the subset has at least n plus 1 elements, then it contains at least 2 elements, one that divides another. If we choose 55 numbers from the set 1 to 100, whenever you see something like this, you always want to ask yourself, why 55? Why 100? There's probably some relationship between them. If I give you 100, there's probably some critical threshold where the 55 is coming from. Then among these numbers, there are 2 whose difference is 10. Choose n plus 1 distinct integers from 1 to 2n. Prove 2 of them add up to a number that's a multiple of 2n. If we require the 2 numbers to be distinct, then we would have to have n plus 1 numbers, okay? And then let a1 through an be integers, prove that there is a subset whose sum is divisible by n. So no matter what integers I give you any n integers, we can always find a subset whose sum is a multiple of n. So do any of these problems look interesting? Which one? I saw you nod first, so you win.
All of them are pretty.
Okay.
I think that the easiest one, I mean, don't make me do it, but the easiest one intuitively is the second one.
Okay, so let's do the second one. What do you think is going to be useful to study these problems? I think you just said it. What do you think is going to be useful? What's today's topic? Well, it was sum of squares, but what's the main? We were using sums of squares as a springboard to talk about what? No. Maybe it's not so clear. I wanted to use these arguments because it gave me a great opportunity to introduce a nice proof technique. What was the big proof technique we used? The pigeonhole principle. So these are 4 continuations of the pigeonhole principle. These are 4 different ways to use it. For the pigeonhole, you have to figure out what are the boxes? What are the pigeons? Sometimes it's not immediately clear what is the box, what is the pigeon. So you said the second one looks interesting. So we take 55 numbers from 1 to 100. Then among the chosen number, there are 2 whose difference is 10. Is this problem well written?
No.
No.
Well, it's at least 2, right?
Well, 2, okay, so again, for mathematicians, sometimes that's actually acceptable.
Okay.
So years ago, I was visiting some family in Maine. And as you do in the summer, you talk about the Red Sox. And chatting with my neighbor, so with the neighbor of one of my dad's first cousins, and the neighbor casually mentions the first time the Red Sox gave him a World Series championship ring. If you've only been given 1 World Series championship ring, can you still say the first time? Yes. If you're not a mathematician, would you say first time if there wasn't a second time? No. No normal person. Like, how many rings do you have? Do you want to see them? Yes. So I'm not going to say more because this is being recorded. So a lot of times there are, in natural speak, implications you make from word choices. Right, and so, the story of, there's a lot of stories about Wigner. One of them is that when he was moving, his wife asked him to make sure that nobody takes the luggage while she goes in to check. There's 10 bags, watch them. And when she comes back, he goes, I'm sorry, one of the bags is missing. What? There's only 9. I left you outside for 3 minutes. Well, count them yourself. Look, 0, 1, 2, 3. The other story that has to be mentioned, as long as you're talking about him, is his wife was afraid that he would forget that they had moved. And she'd really negative says, I'm not a complete basket case. I can remember we moved. Let me write it down for you. No, I don't need you to write it down. I can remember the new address. And so, of course, he forgets and goes home to the old house and doesn't remember where they moved. But fortunately, he sees a little girl in the distance and he goes up to her and says, excuse me, I'm Professor Norbert Wiener. I used to live in this house. I was wondering if by any chance you happen to know where I moved. And there's several variants. My favorite variant is the girl goes, yes, Dad, Mom thought you'd forget. Other variants, he does recognize that it's his own daughter. But anyway, mathematicians would not take any issue with saying first if there's only 1. Most human beings who are not mathematicians would never say that. So when you say if we choose 55 numbers, what do you think is implied in that choice of 55 numbers? Distinct. So what if they weren't distinct? Would there have to be at least 2 whose difference is 10?
You choose 55 ones.
You choose 55 ones. So this is a bad problem. So if we choose 55 distinct, do not be afraid to say something is wrong. Just because it's written down doesn't mean that it's right. So we will now choose 55 distinct numbers from 1 to ... 100. Claim to differ by 10. How many differences do we have? So how many differences, let's say positive, do we have?
Asking for exactly 10, right? Not at least 10.
Not at least 10. I want 2 numbers who differ by 10. So my first question is, if I give you 55 distinct numbers, how many differences do I have?
5 choose 2.
55 choose 2. Why is it 55 choose 2? And when I'm doing it like this, I'm implicitly saying I'm choosing 2 numbers, and I'm not going to worry about is one number larger or smaller.
No, it's divided by 10.
Well, is it divided by 2 or not?
It's not.
It's not. This is the number of ways to choose. So this, chooses a pair of numbers. And we can label them X, Y, with x less than y. So how big is 55 choose 2? It's 55 times what? Over 2. All right, so that's going to be 55 times 27. And did somebody whip out their calculator? Or do you need me to do it?
1,485.
It's how much?
485.
So how does this help us?
Choose from two. The overall number of different pairs of numbers whose difference is 10.
Okay.
I guess you go, what are all the possible distinct?
Okay, good. So how many distinct differences are there? How many distinct?
So
Differences.
185 is the pigeons, and then the distinct differences.
Well, it's the potential pigeons.
Oh, you're right.
We have not officially declared our pigeons and boxes yet. And so right now I'm just doing some cursory exploration to try to get a sense of what might my pigeons be. What do I have? I know that if I have 55 numbers, I'm going to have 1,485 positive differences. How many distinct differences can you get from numbers from 1 to 100?
5,000 approximately.
I'm sorry?
5,000 approximately.
I don't think so.
Wait.
We have the numbers from 1, 2, 3, all the way up to 100. How many distinct positive differences can we get? 99. I can do 100 minus 1, 100 minus 2, 100 minus 3, all the way up to 100 minus 99. I can get any positive difference from 1 to 99. Can get 99, 98, 97, ... 2, 1, or 99 possibles. I care about 10. So again, I may be trying to mislead you. We need to figure out what are the pigeons, what are the boxes. Your one possibility is we have 99 possible differences. We have 1,485. Is there going to be some box that's hit twice? Yeah. So we definitely know that there's a box that's hit twice, but that may not help us.
There's also, I don't know if this makes sense, but there's some boxes of different size. So like 99, can only be hit once.
Yes.
Whereas like 98 could be hit twice. 97 could hit 3 times.
Right.
So you have like different. So even if multiple pigeons want
Good.
another 99 that can't.
But this is now going to become a very involved. Now, again, it's possible that that's either a solution or the solution, but it seems very complicated.
Yeah, it is.
So the reason I like this problem is it's not immediately clear what the pigeons and boxes should be. I think when you're looking at the most natural thing is how many pairs of numbers do we have? We have 1,485. How many distinct differences do we have? We have 99. So at least one of these differences is hit many times. So for example, I might know a sub 7 minus a sub 6 equals a sub 11 minus a sub 8. Who cares? That doesn't necessarily help me. So another way to look at it is we could try to construct sets that either have or don't have numbers that differ by 10.
That's what I was thinking. I just couldn't. I don't know. I was trying to solve them.
Yeah.
You just can't do it.
Okay, so, and again, whenever they give you a problem like this, if they give you numbers like 55 and 100, they're probably nicely related. There's probably something critical going on. So if I give you the number 1, what do you know?
Well, now you can't choose 11.
You can't choose 11, but you could choose 12.
Then you can choose 22.
Right. So if I look at numbers that are congruent to 1 mod 10, I can choose every other.
Yeah.
Can we do this for each congruence class mod 10? That the best we can do is to choose every other. So let's break into congruence classes mod 10. How many congruence classes are there mod 10?
Are we breaking down the numbers or breaking down?
Well, we're breaking, we have 55 numbers that we have to choose from 1 to 100. And for each of them, we can look and see which one of them have remained a 0, which ones of them have remained a 1, which ones of them have remained a 2. So how many congruence classes are there mod 10? 10. So we have 10 classes. So remainder 0, remainder 1, ... remainder 9. And for each one of these, what's the maximum we could take? 5. We can't take two things, right? So we could take, well, we can't do 0. So we could do 10. We can't do 20. We could do 30. Can't do 40. Could do 50, 70, and 90. For the next one, we could do 1. We can't do 11. We could do 21. Can't do 31. Could do 41, 61, 81. And again, if we didn't have 21, if we had 31, then that would just lead to something that's not going to have more things. Does everybody see that if I don't have 21 and I had 31, then that's just pushing myself back even further. So for 9, it's 9, 29, 49, 69, 89. And each one of these has 5. Right? So how many numbers does this account for? Accounts for 50. So we have 5 more numbers to put in. So anywhere we put, so do we really need 55?
That's what I was confused about. Why is it not 51?
So if I was writing a problem like this, I would deliberately not do the minimum number needed.
Okay.
I'm sorry? Right. And so you don't want to give away any information. So my question to you is, do you need 55? Can you do it with 51? You could write a computer program and just do some things, short numerical simulations. Can you come up with a physical construction where it fails? So the question is, maybe, this does not seem like a full vigorous proof to me. And that's a great way to end the class, right? This gives you something to think about, is, if we push things a little bit, and then we start trying to add these things, is there going to be some trouble? We can have a lot of things clustered from 1 to 9 and then miss out the next ones. But now when we have to shove something in, it seems like we have trouble. And so it feels like 55 is too high. If we have a configuration like this, there's no way I can add a number and it's not going to be, this set is great for something like that. But notice we're not using anything between 99 and 100. All of those numbers are not being used. Would it be better to choose some things around there? If instead of 90, if I replace this 90 with 100, I can't do anything at 80, I can't do anything at 90. But it does give me a decent sized window. If I replace this 81 with 91, again, I've got some trouble with putting anything in between. And so these are just some thoughts as to, can you make that work? So I will leave this for you to think about. Can you prove that we really only need 51 numbers and not 55? given that there's already a typo in the problem, maybe there's a second typo. But what I like about this problem is it's not immediately clear what are the pigeons and what are the boxes. To me, the most natural pigeons are to look at all the possible differences and then looking at what bins they're going into. But it's somehow we have to use the fact that it's 10. So we'll do more pigeonhole problems on Monday. Pigeonhole problems are fun to think about.